All right, so yesterday we took a look at the acceleration due to gravity. We established that the problems that we deal with when we're talking about the acceleration due to gravity are essentially the same as those that we've been dealing with over the last several days, really over the last week. The only difference is that we always have an acceleration now. What is that acceleration? Always? Always negative 9.81? Yes. We're always going to assume it's negative 9.81, at least if we're on the surface of the Earth. If we're somewhere else, maybe it's a different value because of the mass of that planet or the mass of that moon or whatever the case may be. But on Earth, even though it varies a little bit depending upon where you are, we'll always assume that it's negative 9.81 meters per second squared. Now, explain to me why when you drop say you drop the set of keys like I did yesterday, you drop a piece of paper that's not crumpled up. Explain to me why the piece of paper that's not crumpled up will not accelerate at 9.81. Explain to me why it's a different rate of acceleration than the 9.81 of the set of keys. Yep. Because of air resistance, right. The lighter something is, the more air resistance that it encounters, and the more surface area something has, the more air resistance it encounters as well. So when you drop that piece of paper that's not crumpled up, it's got kind of a double whammy, right? It's very, very light, and it's also got a lot of surface area. So there's going to be a lot of air resistance. We can't use the acceleration of negative 9.81 in a case like that. But all the problems that we'll see involving free fall, we'll assume that there is no air resistance. And that's going to be a reasonable approximation for the most part, because we're going to be dealing with things with very little air resistance. All right, the equations that apply, well, they're group B equations, right? Because we're dealing with acceleration problems. Other than that, exactly the same type of problems as we've done, as I say, over the last week. 2 questions, actually I believe it was 3 questions for homework last night, on page 58. Any issues of those questions on page 58, please? I heard somebody say all of them, actually. Sorry? 2 and 3? Okay. You know what? Let's take a look at all of them. Okay, let's take a look at all of them. Maybe what we'll do, because there is 3 of them, maybe what we'll do is set each of them up, you know, with equations and so on, rearranging and so on. We'll kind of avoid the substitutions and avoid actually finishing it off, because in all likelihood, it's a matter of getting them set up that's the problem. If somebody's having a little bit of trouble getting the right answer after it's set up, then we'll go and we'll do it in its entirety. But if we don't need to do a part of a question, if the problems lie elsewhere, then we'll do only what we need to do. All right, question number 1. It says a rock takes 0.750 seconds to hit the ground after being thrown down from a height of 4.8 meters. What's the rock's initial velocity? Clearly we've got a time of 0.750 seconds. Tell me what the 4.80 meters is. Tell me what that is. Yeah, it's going to be the displacement, almost at least. What's really the displacement of this rock? It's negative 4.8 because it goes downward. Now, height's a scalar, so height's going to be a positive value always. But displacement, if the rock falls downward, is going to be negative 4.8. Hey, what if I threw the rock up to the top of this cliff? What would the displacement be then? It'd be positive 4.8, right? Because then we'd be dealing with a positive displacement. We'd be going upwards. We want to determine the rock's initial velocity. Do we know what the final velocity is? Is it 0? No, it's not. Or at least we're not told that it's 0. We have to assume that it's not. Is there anything else we have if we read between the lines here? Hogan? Okay, the acceleration is what? Good. Acceleration always for these problems is going to be negative 9.81, right? All right. It's a group B question. Obviously, there's acceleration here. Which of the group B equations is it that we're going to use here? At least that we're going to try first. Good. Yeah, let's try this one. D is equal to VIT plus 1/2 AT squared. Is it going to work? I think it is. But in the end, if it doesn't, I'm going to try something else, right? We have D, we have T, we have A, we have T squared. We're just solving for VI, so it does look like it's going to work here. How do we get rid of, what do we get rid of first here? What do we get rid of first? What's not attached, which is the, right, and how do we take that over? Good. So it's going to be d minus 1/2 at squared equals VIT. Now we're going to get rid of the t by, somebody said it? Division, yes. Take it over by dividing. So it becomes VI is equal to delta d minus 1/2 at squared over delta t. We'll plug our numbers in there. Don't forget that it's negative 4.8 when you plug it in there. The acceleration is neg 9.81. When I subtract 1/2 at squared, in effect what I'm going to end up doing is adding, right? Why am I going to essentially add that term? Who can answer that for me? This term right here that I'm circling in red, negative 1/2 at squared. But in the end, I'm going to end up basically adding it. Why? Because you have a negative acceleration. If you're subtracting a negative number, then what do you get? You get a positive value, right? And then, of course, we divide that by t. Don't forget to square the t up here. When we do that, we should, I presume, get the answer that's in the book there, negative 2.72 meters per second, and that negative, of course, means that it's downward. If you have trouble getting that number with that rearranged equation, then let me know, and we'll show the substitutions. If not, then we'll move on to question 2. I know when you guys were working on this yesterday, number 2 seemed to be giving people a little bit of trouble. This is the one where a lot of people were asking if VF was equal to 0 meters per second, because when it hits the ground, right, it's got to stop. Why is it not? Why is the velocity, how do we know the velocity is not 0 meters per second as it hits the ground? Sorry? Yeah, with the demonstration we did yesterday, it hurts, right? If you throw the hole puncher down on somebody and it hits them as they're lying on the ground, it hurts. Why does it hurt? Because it's moving. It's got kinetic energy, it's moving. If it wasn't moving, it wouldn't hurt. All right, let's get rid of this. And let's try question number 2 now. Having scored a touchdown, a football player spikes the ball in the end zone. If the ball was thrown down with an initial velocity of 2.0 meters per second, we're going to say VI is negative 2.0 meters per second. We're going to say the displacement is negative 1.75 meters. And we're going to say the acceleration, as always with these questions, is neg 9.81. We're looking for delta t. Now, here's the thing that gave people trouble in this question. A lot of people said for this, well, d is equal to VIT plus 1/2 at squared. Is that a valid equation here? Are you allowed to try that? Sure you are. And in fact, there is only one unknown in this equation. It's delta t. So that should mean that we should be able to use this equation to solve for what we're looking for, delta t. The problem is, because there's a t and a t squared in there, unless you know something called the quadratic equation from math class, you can't do this. The quadratic equation goes x is equal to negative b plus or minus b squared minus 4ac over 2a. If that looks like another language to you, then you have no hope of being able to use that equation to solve this problem. None. I'm not going to teach you this equation right now. If you've used it before, you can use this equation to solve for delta t there. But if you haven't, yeah, again, you got no hope. So let's try something else. Let's try something else here. Let's try VF squared is equal to VI squared plus 2AD. Just picking an equation. I've got VI, I've got A, and I've got D. That allows me to solve for VF. It's not what I'm looking for, but it's something. When I can't get what I'm looking for right away, then get something. Get something. Square root of VI, or square root of VI squared, it's going to be 2.0 squared. Why did I drop the negative there? Why didn't I say negative 2 squared? Although negative 2 squared is going to be the same thing. Why did I drop the negative? No, that's not why I dropped it, although it will be. No. No, Sarah? Right, good. This is speed. It's a scalar. It doesn't have direction. So it's going to be positive 2.0 squared. This is still going to be neg 9.81 because it's a vector. D is going to be neg 1.75. Because it's a vector, it's going to be negative as well. Let's get the value of VF there. We get 2 squared plus, let's do some brackets here now, 2 times neg 9.81 times neg 1.75. Get 38.335. Let's square root that. We end up getting 6.1915. Okay, that's VF. VF speed, VF velocity would be negative 6.1915 meters per second because it's downward, right? Throw a football downward, which way is it moving at the end of the problem? Downward. All right, does that help me? Do I now have enough to solve for delta t using another equation that I won't have to use the quadratic formula for? Yes? Chase, what do you want to try? Okay. VI plus VF over 2 times t, is that a valid equation, everyone? Sure it is, because it's one of the group B equations. Do I have delta D? I do. I have VI, I have VF. I'm solving for delta t. Looks like it's going to work. So let's take the entire term VI plus VF over 2 over by dividing. It becomes D over VI plus VF over 2 equals delta t. Delta D was neg 1.75 over neg 2.0 plus neg 6.1915 over 2. That should give us our answer here. Watch very closely how I do this on my calculator. Let's do the bottom first. Let's say negative 2 subtract 6.1915 plus equals, whoops, what did I do? All should be, yeah. Okay. Negative 8.1915. Let's divide that by 2. Negative 4.09. And then let's say neg 1.75 divided by that number is 0.427. Is that the answer? 0.43 seconds. Just curious, did anybody who knows the quadratic formula use it? Yes? Did you get the same answer? In fact, you would have got 2 answers, right? In 1 second with that. You would have got 2 answers. You would have got 2 answers because it's negative e plus or minus. Essentially, if you plotted a graph of this, it would have 2 x-intercepts. Okay, so that's why you're going to get 2 answers. And on the x-axis would be time. Okay? So you're going to get 2 times there. What were your 2 answers? 0.43, obviously, and 0.43 and 0.83. What does the 0.83 mean there? Let me think about that. You know what I think? Yeah, I think what it is. I think what that is, the significance of that would be that instead of throwing it, I think it's instead of throwing it upward, downward, if you threw it upward. I think. Not necessarily. You're only throwing it up at 2 meters per second, which means it's not going to go very high. So I think that's what it's going to mean there. Oftentimes what happens when you use a quadratic equation, Michael, is you end up with a, we're going to see a little bit later on in the unit, we do something called projectile motion. The ball goes like this. That's a parabola, right? So it's perfect using quadratic equation then, although we're still not going to have to use it. If we launched it like this off the edge of a building, then you wouldn't have a choice. You'd have to use a quadratic equation. When you find time on this problem, you're going to end up with one value, say 0.4 seconds, and another value, negative 0.2 seconds or whatever. So that's going to be pretty clear which one is the which one is the one you're supposed to use there. That's a bit tricky. Yeah, 0.4 and 0.8, that's a little bit tricky as to which one you use, for sure. Just out of curiosity, I'm like, do you know what the negative 0.2 would represent in this case? You throw a ball right here. It takes 0.5 seconds or something to take this path. The negative 0.2 seconds would be, if it went backwards right there. But, I mean, like I say, that's for another day. And it's easy to determine which one is the one that you use anyways when it's a negative value, right? Okay, copy that down if you don't have it already. It's a tough question. It's a good question, though. All right, let's take a look at question number 3 now. Let me erase this stuff so we have some space again. All right, question number 3 says an elevator moving downward at 4 meters per second experiences an upward acceleration of 2 meters per second squared for 1.8 seconds. What's its velocity at the end of the acceleration? How far has it traveled? VI is going to be negative 4.00 meters per second because this is downward. A is 2.00. A in this case is not 9.81 meters per second squared. Can anybody explain to me why it's not 9.81? How come the elevator doesn't fall at 9.81? Yeah, there's a cable, right. It's not just gravity that's acting. Okay, it's 9.81 when you're under the influence of just gravity. And for most of the problems we do involving changes in height, that's the case. But clearly this one, it's not. You don't want your elevator to free fall. If your elevator free falls, well, remember that it's not moving at 0 meters per second when it hits the ground. So you're in a little bit of trouble if your elevator free falls. It's got an upward acceleration of 2.00 meters per second, though, squared. What does that mean? How can it be moving downward, but yet have an upward acceleration of 2.00? Yeah. Right, when you're moving downward, but you have an upward acceleration, that doesn't mean it's moving upwards. It just means that the acceleration is in the upward direction, which means if you're moving downwards, you're slowing down. And so this elevator is slowing down at 2.00. We've got a time of 1.80 seconds. We're looking for the final velocity, and we're also looking for the displacement, how far it's traveled. What do you want to do to find? It doesn't matter what order you do these in, by the way. VF first or delta D first. What do you want to try first? Delta D. Okay. What do you want to do? Okay. Yeah, that should work, I think. VIT plus 1 half AT squared, negative 4.00 times the time of 1.8. 2.0 times the time of 1.8 squared. Let's get a value for that. Multiply those together. We should get 3.96 meters, right? That's the answer in the book. What about VF? What about VF? Yeah, that's what I saw right away as well. A is equal to delta V over delta T. Let's solve for delta V. The T goes up by multiplying A times T. It's 2.00 times the time of 1.80. That's going to give me a change in velocity of 3.6 meters per second. But delta V, that's not what we're looking for. Delta V is equal to VF minus VI. VF is equal to delta V plus VI. It's 3.6 meters per second plus negative 4.0, which gives me positive 0.400. Negative or positive? Negative, right? Because we take the VI. The question was, if you didn't hear it, guys, if delta V is equal to VF minus VI, how is VF equal to delta V plus VI? Well, it's equal to delta V plus VI because we take that negative delta or negative VI over to the other side by adding, right? Subtract it from the right side, take it to the left side by adding. That leaves us with delta V plus VI equal to whatever's left there, which is VF. How did I get positive 3.96? Okay, let's go through that. Oh, you know what? I think it is going to be negative, actually. Yeah, I think it is going to be negative because it's moving downward, right? I just took the answer that was in the book. Kind of cheated, but let's calculate it on the calculator, okay? Just to make sure. It should work out, you're right, it should work out to be negative because it's moving downward. But let's make sure mathematically that it does. Okay, let's say negative 4 times 1.8 is equal to negative 7.2. Let's add to that, put some stuff in brackets here, 0.5 times 2 times 1.8 squared, negative 3.96. Yeah, you're right. I guess they put positive because they were simply looking for how far it traveled, the distance, a scalar, and I just didn't even think of that. We solve for displacement, they solve for distance. Right? We're good with those? All right, let's take a look at just one more example here today. 1.18, page 59. A clown throws a ball upward at 10 meters per second. Find the maximum height that the ball reaches above its launch height in the time that it takes to do so. I like this question. Not because it involves a clown. That only adds to the excitement of this question, let me tell you. I like this question because you got to read between the lines a little bit on this one. And those are the questions that I really like, when you got to think a little bit, read between the lines a little bit. VI is 10 meters per second. That's easy enough. And it's positive because it's upward. A is neg 9.81. Even though this ball is moving upwards, the acceleration is neg 9.81. Why? Right. It's slowing down. As it moves upward, it's slowing down. That's a negative acceleration. Good. The maximum height that the ball reaches above its launch height, what's that? What are we really looking for there? We're looking for the displacement, and we're looking for the time as well. Is there anything else that we have if we read between the lines here? Yes. Can you explain to me why VF would be 0? Good. Perfect. At the top of the path, it stops. And then it very, very quickly turns around and goes in the opposite direction. But this question is only asking me to analyze the trip up. So if you're looking at the trip up, it is going to stop at the end of the problem. VF is going to be 0 meters per second. I don't care which one you find first, D or delta T. Even though the questions are separated as A and B, you get something like this on a test and you solve B first, that's absolutely fine. What do you want to do? Which equation, which variable do you want to solve for first? D or T? Time? You know what my first thought was? My first thought was actually D is equal to VIT plus 1/2 AT squared. But then as I thought about that equation, D is equal to VIT plus 1/2 AT squared, thought, well, it's a valid equation, but I got two unknowns in there, right? So that's not going to work for me right away. Might be able to use it in conjunction with something else. You might be better off solving for time here first. What did you use? Yeah. Yeah, honestly, I think that is the way to go with that. Let's turn around and rearrange that, solve for delta T. Becomes delta V over A. Delta V, VF minus VI, 0 minus 10. A is neg 9.81. It's going to give me a time of what? Negative 10 over neg 9.81. Uh, 1.0194. which, let's round that to 3 digits, 1.02 seconds. Look back at our original data. We've got 4 digits here. We've got 3 digits right here. Final answer should have 3 digits. Now let's solve for the displacement. Lorene, I can use that equation that I thought of first now to solve for the displacement, or there's probably another way to do it as well. VF squared is equal to VI squared plus 2AD. That's the one you used? The one I used? Okay. Doesn't matter, right? VI is 10. Delta T is, we just found it, I guess, 1.0194. Okay, let's solve that. Let's say 10 times 1.0194. Let's press equals. And then let's add to that, inside some brackets, 0.5 times negative 9.81 times 1.0194 squared. We get a value of 5.09 or 5.10. 5.10 meters. Is that good? All right, copy that out if you haven't already. And then once everybody's done that, I'll flip the page, show you a couple problems to work on, and then that's going to be it. That's going to be your only homework for the weekend, other than your quiz, that is. And you can have 4 or 5 minutes to work on it in class. Oh, look at that. Good news. Good news. 1 question. You should get this finished up in class. So you got 5 minutes. Finish it up. No homework for the weekend other than your quiz on Monday, which I do want you to review for, because it's not this stuff. It's stuff that we've done a couple of days ago with those velocity time graphs. So you do have a little bit of homework, and that's reviewing for your quiz. But if you finish this, that should be all that you have for homework. All right, let's get this done.